Our speaker this evening has quite a long history of credentials. He was formerly the CEO of IBM's Object Technology International Labs. He's also the godfather of IBM's Smalltalk and Eclipse. He's the chief scientist for KX Labs. Let's give him a great big round of applause, please, to Dave Dobbs.
Thanks so much, Eric. It's a pleasure and a privilege to be here in New York during Database Week. See the lineup you have, and I'm very impressed. I'm not actually sure. It must have been a cancellation, so you put me in. Just before I go on, just a couple of disclaimers. First of all, if you're here because you're a KX fanatic, you're probably going to be disappointed, as this talk is for a broader audience. It's a database audience, and I won't give you any more skill testing questions. It's actually, I think, 12 or 13 characters for Sudoku. I wanted to talk about lines. The title went from, I know I'm dyslexic, but I believe there was some machine translation applied to my title and converted from Canadian to American and made it into this most boastful title. So it was a little more humble, but I'm used to putting my foot in my mouth, so it won't be a problem. I'm really coming at this not from a database guy point of view. I'm really a consumer of databases and have been for a long time. So in some ways, this is really about how I think they should work if they ever ask me. This is if you're a software guy and you've worked with electrical engineers, you know that often they'll come and ask you, how would you like the hardware to work? And then they ignore you and do the easy bits and let you do the stuff in the software. Well, I think that's often true of database implementers, and sometimes they seem to leave some things out. So if nothing else, I'll be able to perhaps talk from this perspective of the user. I will talk a bit about KDB, but I'll keep it to a minimum. And I am, unfortunately, in a public company, so anything that I'm saying is really my personal opinion. I'll just leave it at that. My background, I've really only been with KX for 6 months. I sold them a small R&D company that I had called Madera Research Labs. Some of you who know of me, I've been trying to find a way to build software with a small number of people, the smallest number of people possible, as quickly as possible. And I keep leapfrogging technologies, and I managed to, I've pimped more strange languages to companies than probably anyone else. And I think the only reason you get to do that is if you ship. So we have a great tradition of trying to find the shortest path to get things done. And that's really why I appeared. Only briefly I got stuck at IBM. Not that being at IBM was bad, but I did have a Java journey, and I'm afraid I did build Eclipse. And that was very painful, since it was 10x what it taught. It was the same thing we built in Smalltalk, except slower, way bigger, and cost 10 times as much. But, so I apologize for those of you that are still using Java. There are people still using COBOL. God forbid, there's a lot of people in this room that are still using APL, so you Java guys are way ahead. So basically, the way I got involved with KDB, although I've known the community for many years, since I briefly did APL in a previous life, but more recently, I was involved with a large customer that had to look at a lot of cyber packets, and in particular looking to try and identify cyber attacks, or so-called, simply called zero-day attacks. And the problem with zero-day attacks is that people don't actually go around and say, they don't have story cards like all that crappy Agile junk, right? We write down what the story is going to be like, right? Please get over this, right? It was a simple idea. I'm sorry I was involved with that too, right? Agile objects, just go away, please. Something just stick around too long. So the big challenge was basically, how can you build an environment that has to look at a lot of data very quickly, where the analysts, the cyber analysts, have to be able to do this. And the way they do it is they basically hypothesize what different attacks are going to look like. In business, we call this predictive analytics. Stock market is basically what they do in trading. So, well-known problem in your world, for many of you. And basically what you do is you construct models and say, well, this is what we think an attack might look like, and here's the kind of fingerprint it might look like, might have. And then you deploy those out into the world, and every once in a while, number 449 goes off, and then you have a problem saying, oh damn, it really looks like this horrible attack that I thought probably would never happen, but I had to make it up because I just thought of it, and all of a sudden then you have to deploy that very quickly into an infrastructure. So that also meant that we had to be able to have something that was deployable into an embedded world so we could deploy it through routers, network nodes, globally. So it was a really fun problem. And we went through a lot of technology solutions, and we found out that the only thing we could use was this thing called KDB. We had to build a lot of tools on top of that. Fortunately, I spent most of my life building bad tools and selling them to other people to use. My apologies if you're using Eclipse. IBM cut the funding out almost 15 years ago, so that's why IntelliJ is a much better product. So that was really my background, and I ended up coming in really as a customer. And then after we built this environment, it turned out that people thought that other people should be exposed to it, which is kind of cruel for most KDB guys because they're hardcore black screen programmers. The last thing they want to see is an IDE, get that stuff out of my way, right? I mean, the badge of honor today is a black screen. But what we've done is basically work on tooling for normal people who don't know how to use a tool like KDB so they can go. Anyway, that's where I come from. So very briefly in history, I want to take a moment here in history. I know I won't spend long going through this sort of history of data, but because I'm in New York, I want to give testament to the fact that many of the hot ideas that are cool in California actually came out of the financial community and have not been recognized. And so at least I can do that here and pay tribute to those people who thought of those ideas. And of course, no idea had a unique birthplace. These often happen in parallel. We know Tesla was really the first one, don't we? So we really go through this. So basically, we started off, and then we got B trees, we just had flat files. The first column store, what I think was MIT in the late 60s. The key files, or BSAM, you might know those today. Ever heard of a key file? It's a key value store. What an idea. Breakthrough. Hierarchical databases, conceptual and physical data models. That's when we actually have a model for the data as opposed to just the data. That's what an idea that is. So you can actually tell what it's possible to join together and whether it makes sense. Today we seem to have tossed the data model in the bin. Well, you don't need to worry, NoSQL, you just toss the whole schema away anyway. So you can query it whatever way you want, ask any question, get any answer. Then we had 4GLs. This was really the enlightened period. We had 4GLs, an APL, and normal people, well, not the APL guys quite, they're not really normal. But both of these groups, once they crossed the barrier, could be very, very productive, particularly the 4GL community. Normal people able to sit down, build their business applications without having a master's or a PhD in computer science. And very, very productive period, very exciting time. But unfortunately, the 4GL vendors took a lot of money away from the major vendors. And major vendors don't like that. So they found out there was an inferior technology called relational database. And if they all standardize it, then they can convert everything back into a platform game. This is exactly the same game that happened with web services, right? The major platform vendors want to control the stack. So you have to use our stack. So they disappeared very quickly. APL, because it ignored databases, disappeared very quickly. It also, of course, required that you have a special keyboard. Just think today with Unicode, it could be back, guys. I can tell it, wow. And then we had network databases. You might know those today as kind of graph databases, pointer connected data structures, or if you saw them in a midlife crisis, they were called object-oriented databases. You actually look at the pages on disk, you couldn't tell the difference between anything. Way back in 1978, Gardner has this new word called HTAP, which is basically an RDB plus a HDB, or the Lambda architecture, or a translytical database if you're forced. They're all the same thing. Basically the notion that you have the data that you had that's done, it's immutable, which is the history, or batch, we call it the Lambda architecture, and you have the data that arrived today, the new stuff, which is called the real-time database. And you get consistency very simply by doing a query against both of them. And you can bring those together at whatever speed your infrastructure can support based on your data volumes and so on. Frequently it's overnight. In some cases, people are able to do it every few hours. Fortunately for the stock market, there's a window whereby they can actually cause that, be able to bring the historical database up to speed. The first one was actually done by Arthur Whitney for the official airline guide in 1978. And I was just talking to Arthur about this, and he said, yes, databases are getting really small. He said today, if the official airline guide had actually grown at the rate that storage had grown, it would be a quadrillion rows. It is very interesting, databases relative to the amount of memory we have are getting a lot smaller. And that's going to be a bigger point later. And we had OLAP and logic databases, a lot of things that just went away, object databases, which was always a bad idea. And then we came to the decade of disappointment. Right. Sometime around this time, we all realized that, yes, we had Oracle, we had Sybase, we had DB2, and life sucked. Of course, we had the object zealots who wanted to spend a lot of, we want to speed up your mid-tier Java server. It's very easy. Delete the object or relational interface. Just delete it. You can make 25 grand doing a performance improvement for somebody. Walk in, delete that, and delete their serialization mess, and you probably sped it up. Big problem. The rows, object databases, XML databases, they're really just a niche. The rows are too wide, so we have to pull them all into memory, even though we only do care about, and boy, do we make them wide. Were they called database administrators or data moonies? I'm not sure. I've seen so many tables in some of these data warehouses, it's an uncountable number of tables. I worked at a large bank, not in New York, and they had 57,000 entities. I asked them where they got the names, because most people's dictionary doesn't have that many names. This is why data semantics is such a problem. We had stored procedures. Stored procedures, of course, give you a little bit of performance, but they're really not fun to debug. And of course, if you're an agilista, you just hate stored procedures. As long as also you hate the database and everybody else will do with databases because they slow you down. XQuery, RDF, good for government work. May the semantic web come to us all someday. Knowledge representation ontology, none of that helps us. Oh, guess what? 32 bits lets you address 2 billion rows. What happens if I have more? Suck it up. You need to be a data architect. You have multiple databases, and then you can join them. Well, the next thing we have is basically the database is a monolithic black box. You get, only the DBAs know it, and the query optimizer. The query optimizer works so well, there's courses to understand what the guts of the query optimizer is doing. So you can debug it and understand it. But this was really just before. It just got worse and worse and worse. No semantics. Oh, the data warehouse. That's the most polite name I could use for it. Basically, $2 million, you get nothing, a broken star schema, and the ETL isn't working. 90% of the data warehouse projects that I've been involved in. Asset transactions are expensive. They're not available if you want to do them globally in a distributed way. No implementation. Cheap search, all these things we want. And then of course we have the whole cloud and cluster scene rising around in the early 2000s at Google and followed by many others, where basically there were lots of cheap processors, but not too much memory because that was expensive, and the disks were really slow because in particular, Larry Page wanted the cheapest cost per search. So they built a very fine-tuned infrastructure to guarantee that no one can do search cheaper than they could. But it's less reliable. And you've seen the stories from Netflix. Basically, they have a lot of infrastructure to be able to do this. So this demands things like replication and so on, to be able to add the fault tolerance, which you would other get in a sort of 5.9 system from a telco design, but that would use different specialized software. And of course, if you want to use SaaS, if you really want to be Salesforce, you want to be calling up Larry and saying, Larry, I don't want to pay you for all these instances. So what I want to be able to do is multiplex all those things together. And the shocking thing is how many people allowed their data to be mixed by the key of their customer name in the same pool of database as the other people in Salesforce. Until recently, where it's done more properly in Oracle 12, where they actually partition the multi-tenants into separate partitions, which is the way you should do it. So meanwhile, during this time, Arthur Whitney was in the 90s, and he had this new programming language called K. Arthur just numbers them. He's currently on K6. And he invented, somebody said, look, Arthur, you can't sell a programming language, so what you need to do is sell a database, which was a really good idea. We definitely would not be here today, especially in the world of open source languages and every runtime is free. Very difficult to be successful with a runtime infrastructure today unless you have significant backing, like a sugar daddy or something like that, that is backing your open source project. So what he did is built a unified vector programming language into a column store. Very simple idea. Had a somewhat cryptic vector language, not too cryptic for the crowd over here, but it has been described rather rudely as line noise. And it's like many things. Once you know how to speak it, it's a wonderful language, but not everyone knows how to play an organ. And but some of you have actually gone through a lot more to actually get your Emacs or BIMAC book. And they don't do anything for you except move the screen. So this showed one of the interesting things that was in that language is first-class constraints. One of the big challenges with doing GUI and distributed systems and so on in general, but GUIs in particular, is this whole model view thing. There's all these reactive frameworks and so on. The nice thing about two-way constraints is they basically have a very simple programming model that allows the GUI to reflect what's in the model, and vice versa if you change the GUI. So this is a very elegant solution to a problem that's still pretty thorny. All of you that are trying to get RX working and so on, it's a challenge. And of course, it allowed financial markets to process a lot of tick data, and that's why KDB took off. Following that, Arthur, in true tradition, said, well, that was a good idea, but it had so many things wrong with it, it needs to go in the bin. One of the brilliant things of KDB is the underlying core technology actually changes. So that basically Arthur, unlike many people who have a programming language, say, well, we have to be compatible with the previous one so we can preserve all the bad ideas and add some more ones. You got lambdas in your Java and your C++ now. Whatever you want to add. Generics, let's have some of that, plus some of this, plus some of this, and pretty soon you have Ada or PL1 as they get more and more junk in. So one of the brilliant things that Arthur does, somewhat challenge for customers, but that's isolated by having a DSL on top of the underlying runtime. much as the AS400, which is a very successful machine that was very data intensive. Basically, the processors and everything changed under the AS400, but none of the customers were aware of it. Gives you a lot of choices to change your fundamental bindings at the bottom of the system and not going to protect your customers from those changes. So on top of that, he implemented a new language and he built a DSL so that normal people could use it. Q is a keyworded DSL, really designed for capital markets. And he built a regular SQL on top of that, so those people could do whatever you can do in SQL 92, which takes you back into the bad, the data winter. Or you could do QSQL, which gives you implicit joins, implicit group bys, window joins. So you end up, when you write SQL, you end up with about half the code that you would if you were trying to write that in any other dialect of SQL. There's a bunch of other things that are in there that are very important. It has nulls, infinities, and time as a native type. Current implementation is time in nanoseconds. You have simultaneous events, and you have to do them with a millisecond counter, plus a count. Then you get to join on those two columns for a few trillion rows. Watch your performance go in the hole. Plus there's a full algebra of type of operation over all these operations, so you can combine a dictionary with a table. They're all first-class entities. They can have as many rows as you want because it's 64 bits, both in the offsets and in the base. So you can work with lots and lots of data with a simple uniform model. And it doesn't matter whether it's in memory or it's on disk. Clearly you're going to get a performance difference. It likes lots of memory. Fortunately, the world is going that way. So this allows you to basically do this common Lambda architecture, as it's called today, or HTAP, or translytical, where you basically have an immutable batch database and a real-time database coming in, and you can query and work with both of those. The real-time one's often called a stream. What's the difference between a stream and a database? Depends who the marketing guy is. If it's moving and they can be push or pull streams, and that gets you the difference between whether it's reactive X or reactive Y. But in the end, if you can bring it in large blocks, then you're going to be able to process it much more efficiently. So in practice, you're actually working with a buffer, typically in the case of KDB, about 64 KB at a time or bigger. Currently, you can IPC up to a terabyte. I think one of the important things here, and of course it has streaming and pub sub, using tiny processors. Lots of tiny processors doing pub sub. What's that called today? Microservices. Give yourself some credit, guys. It wasn't only done in KDB, by the way. This was done by lots of other people in the financial sector. Many of these ideas that are really hot today in the Apache animals came from you. Or else they were rediscovered independently. It just took them 20 or 30 years. One of the most impressive things for me is that KDB, the web server, the ODBC stack, is 200K bytes of code. It's really that large because of the C libraries. It's actually smaller. It's actually about 80K bytes for the actual core engine. This is very, very important in my world because I want to be able to embed it. It's also very important because it fits in the instruction cache on most modern machines. And this is one of the key factors that gives performance, also the ability to distribute code. Okay, well, there were all these people really fed up with the database winter, and they got together and they said, we hate Oracle. It was really, NoSQL is really not Oracle. But take that the other guys too, but it was a real anti-Oracle movement. And they basically determined, and so they got together and they said, what we need is a brand. We're all completely different, but we're going to make ourselves one brand. So we're going to become the NoSQL gang. And NoSQL is really sticky. So the net went to it right away. There's a ton of these. There's still new ones coming out. Basically, I think you know the features because they've been talked about in this group, and I don't want to bore you with them. Basically, they're often specialized for the kind of application, sometimes a document database, or like Redis, which is a cache database. Very different versions, design points, and you get this rich variety of choice. I did say that like it was positive. Right? And of course, you can shard and scale out. And most of them, look, if you can't query it, you can always search it. And that saved a lot of people in the big data business. I got my whole Spark cluster, but I can put in Elasticsearch and get some results out of my HDFS store because I can't get them out of Spark. Well, maybe after IBM puts another 300 million in Spark, it'll have reasonable. Hey, it worked for Java. The reason Java is fast today is IBM and Oracle both put close to $3 billion into making Java as fast as C++ is today. So, money can do things, money and time. So by 2030, you'll be able to look at your data really fast with Spark. Sounds exciting. I won't be doing it. So there are a whole lot of these things, and at the same time, of course, this was the time of MapReduce, where basically you don't need to use queries, all you have to do is put MapReduce together. And MapReduce is really easy. It's just like doing regular expressions, which are really easy and frequently wrong. And when you let this loose on a large cluster of machines, it can suck a lot of cycles getting the wrong answer. So of course, this was the big NoSQL, really meant no query. You don't need to query it. And it's why young Ruby programmers, other people loved it because they never understood databases anyway. They hated them. So they could just actually squirt the stuff into a blob, and it was no problem. So it was really easy. What they did is they passed the problem on to every other poor bastard that actually had to query the stuff and get data from it, because you have to write a parser for it. You who store things in NoSQL and stuff everything in JSON blobs have to parse and write every report in your company that has to deal with it. Surely we get over this, Binary data is the way to transform data. Anyway, lots of these great things. MapReduce, then people said, maybe we could query it. We'll have a query language, cascading, Pig, Cascalog, and then finally Hive SQL. The slowest way to do SQL that you can think of. Very limited because it's trying to do it with MapReduce on top of the cluster. It's better in Spark, and it'll certainly be better in the next Apache animal because there's a new Apache animal every quarter, or maybe 3 or 4. Now, of course, the big advantage touted by this is, look, we're all NoSQL databases. You just have to choose the right one for your application. So we've got all these different features. So that's a nice thing, because now, along with choosing the 45 programming languages you want to work in, you can choose which of the 45 databases you want to use. Nice idea. Well, clearly, this is the solution. NoSQL. Schemaless JSON. Easy for writers, really challenging for readers. Serialization, move the data, deserialize, parse, all these things. Human readable, but who really wants to read 100K log entries? Or 10 million log entries? Oh, the screen there, look, see, this one's off. I can't even find what's Splunk. How am I going to see with my eyes? Plus, it takes way more space. Now, storage is cheap, and I'm using HDFS, so I'll make 3 replicas. What the hell? Way more storage, way more storage. On top of it, it's way more I/O because you've got to get it from the disks or the store into here. How do we get away with this? We actually drank the XML Kool-Aid and changed the brackets. Nonsense. Without a schema, you'll need machine learning. I just worked at a large company, international, and they're looking at their click streams, And I said, okay, looks like there was a change in the schema here sometime in December by actually running some simple machine learning over the logs to see what they were. It's just statistics, but I know it's now machine learning. And I found out that, oh, well, yeah, we did make that change. So I got to modify the code in the pipeline to actually deal with the schema change. Oh, and by the way, we found about 10 more since. Please, please, use some kind of schema. I don't care whether it's thrift. Version your data so we know which version it is. Just trying to give us a chance. And if possible, just say no to text representations. They're just a bad idea. Now, distributed. Distributed is so cool. I used to live in a corridor with a bunch of top professors who worked in distributed algorithms. And they're so beautiful algorithms. I mean, they're just so wonderfully elegant. They're just very, very hard to get right. One of our students managed to implement one of Tarjan's algorithms. He's a very well-known graph theory algorithm person. And Tarjan actually came to the stage and he said, I never believed it would actually run. They're that hard. Jepson's a wonderful thing. If you're not, it's a testing tool for distributed databases. This is a wonderful website. The other website, Jepson's basically comes from Carly Jepson. This website's called Don't Call Me Maybe, which has to do with the problems when you partition databases. It's tested virtually every distributed database, and I encourage you to go there and beat on your vendor if you're using a distributed database to make sure they've run the latest Jepson tests. It's very hard. IP Sharp, or Ian Sharp, was actually one of the fathers of commercial APL. And back in Ottawa in 1975, I had the pressure to listen to Ian, and he basically said, if God had believed in distributed systems, he never would have concentrated all the brains in the head and connected the rest of the body with a crappy bit serial interface. I still think that's true. So we really need to be able to find a way. There are lots of solutions. I don't have time to go into them, but basically where you can do reliable things. There are some people who really need sophisticated distributed data spaces. I'm not saying they're not useful, but many people end up going for one of these things because they're fault tolerant or something like that. There's lots of ways to do fault tolerance and still maintain performance and reliability. Atomic clocks being one of them, Hardware is actually really cheap compared to software. These are very complicated. Eventually, we'll all get these algorithms working. And there's something that I believe are so important they should be provably verified, something like the Defense Department's doing now for its weapon systems and operating systems to prove that they're secure. But they're very tricky. These are some of my favorite quotes from the High Scalability blog. Basically, you could just see the situation is, very, very naive about people knowing what hardware can do today versus what they end up with very complicated solutions. Okay, well, now we went off and we had the revolution. This is all happening about, say, 2005 to 2010. I don't want to give its precise date because someone will argue with me that they were first, and I don't want to be that wrong. But in that period, there was also an evolution going on. In particular, Michael Stonebreaker, who basically has just received the ACM Turing Award for all his work in databases. If you know him, he's the father of many databases. And he published a very famous paper, at least famous for the people who worked in databases at the time, that basically said, look guys, the way we're doing things is wrong. Essentially what we're doing is we're implementing everything the way we did it in System R. Redo logs, buffer management, B-tree indexes, and so on. And this is wrong for the hardware of today. It's also wrong for the new kinds of applications we're doing. And it also showed that little OLTP chart basically shows how much stuff is actually doing useful work for you. The red is the work that you want to do, the rest is overhead. So you had a reason to be upset about Oracle. They're sucking away all my time. 3/4 of it almost. So that came up with what's known as the NewSQL database architecture. which really came to a series of databases and research databases done primarily at Brown and MIT under Michael Stonebraker's guidance, along with a team of really talented graduate students there. And they created HStore and eStore, and out of some of that work comes VoltDB. And they started publishing the papers, I think it was around 2010, 2012, I don't remember the exact dates. And they realized and said, well, look, we could use a column store, we could have a memory-based architecture, because in the old days, when I started doing database, you only were allowed 3 database, 512 KB database pages in memory at one time. And you had to design your transactions otherwise so you could reliably write those 3 pages of disk in one I/O, or else you couldn't guarantee that you had sort of atomic writes. Now we have gazoodles of memory, so clearly that architecture is wrong. The interesting thing he did is he they found to get real performance, what you want to do is run one-shot transactions. And in their case, they decided to statically compile the transactions and put them inside the database. Oh my God. They're not stored procedures, they're stored functions. Because functions are better now. We don't talk about procedures anymore, everything's functional, so it's good. So this whole architecture changed. The other thing is because the system is more composable and involves less thrashing between stores and so on, with more in memory, you don't have to have a whole lot of knobs to manage it. So you don't need a set of pilots in your data center turning all the knobs for your database. Use replication instead of logs, and it turns out that redo logs on modern architectures aren't the way to go. So it's easier to replicate the commands and execute the commands on parallel machines or replicate the data. And then for ginormous files, they basically, they needed a great name for the paper, I love it, anti-caching. All it is it's the reverse of LRU. It basically says, when the pages get old and you're running out of memory, you write them out on the disk. Of course, it won't be on the disk because there won't be any more of that. We'll come to that. So if you have, basically these are most of the things that Arthur Whitney did in the 1990s, early 2000s in KDB, except they did a few more, like making the data ordered, providing a full algebra and so on top of it. The interesting thing is if you have an architecture like this that's fast enough, well, clearly time series is free, especially with time in your database, and you can do window joins. Multi-tenanted, you can segment things easily onto multiple partitions, and you can separate securely the people that are from one company to another, the Salesforce problem. Since it runs in memory and on disk, what do you need a cache for? We don't need an M cache or a Redis cache plus an Oracle it's just one architecture. You can choose which things you put in memory based on assigning the variables in the appropriate place as opposed to putting them in completely different technologies. Statistical data really is just a different set of functions. The big thing about statistical data is it has missing values, unlike the rest of it. And if you're really smart today, it has things like uncertainty, so you can make decisions under uncertainty. So you can support functions like Dempster-Schafer, which is a computationally efficient technique for reasoning with uncertainty, which is what we use in the KDB solution. A very, very proven technique. Multimedia, sure, you've got to be able to store the blob someplace. You're not going to put them inside the fields in the database. Geospatial, again, you need a set of types to support geospatial. Location's a very, very important thing, and a set of operations over those types. And there is a fairly challenging problem in terms of finding out those things that are near me and so on. There is some really interesting work coming up on some high-performance database there. And genomics, again, maybe you want to go to bit types so you can do the encoding. It's not that difficult to do. Graphs, of course, there's Titan, Neo4j. When you've got scan, right, and you can apply a function in memory, you can actually do graphs very fast. with a database that's got functional support. On top of that, one of the problems in graphs is one of those things where you bet with the devil, right? You bet with the devil that the algorithms you're going to use all want an edge representation. The challenge is there are lots of algorithms that would actually be much better with a matrix representation. Well, if you're in a language that supports both of those, guess what? You can easily mutate the representation on the fly. Today, most graph databases bet edges. Plus, of course, they have to sit on top of Java. They limit addressability. So I don't really understand why you need any of those special data. Data architecture. Now, I'm the first among you when somebody comes along and says, "Hi, Dave, I'm an architect." I basically go, "Okay, are you a post-technical architect, or do you still, can you still smell code burning?" If they can smell code burning, then I want to talk to them. If they're post-technical, I just want to hit delete. Right? Enterprise architect's an oxymoron. I understand you may have it as your job title. Okay. We can't help a company's title. So the challenge is, when you get to a certain scale of data, unfortunately, the database out of the box is just not going to provide an efficient or effective solution for the problem. You can wish it would be true. The salesman will tell you it's true. But when you start dealing with massive volumes, tons and tons of huge data sets with driving at high velocity, should be velocity, volume, you're dealing with demanding response time, where you have to guarantee response to your users at a certain point. You're dealing with global customers, so you've got distributed data traveling through some pretty hairy networks around the world, mobile devices. I'm sorry, you need a data architecture. And the reality is, all the things discussed in here, which I don't have time to go into, fortunately, I've already told you that the Lambda architecture, translytical, whatever the other one is, HTAP, are all the same thing. It's an RDB plus an HDB. And the the most recent one, which is Kappa, by the Kafka and Senza creators, is really a variation of a logDB format. But all of these have been around for a while. They're all really good architectures. And if you can implement them in something that was fast other than Java, it'd be really good. So what's your recollection about hardware? What made it faster? Was it the software? Forget this, you all know the answer. The answer is that most of the time software is saved by hardware. With every new technology, we're able to create more and more. Object technology has created more bloat than probably any other single technology. I would gladly trade anyone, a million lines of Java legacy for 10 million lines of COBOL, because it'd be much cheaper for me to maintain it. The interlock dependencies and so on of object code is really a nightmare. It was a great idea, but we gave out a framework. Frameworks inject dependencies into your program. They're not components. If we'd done what the vision was, which was to make the frameworks into components, then we'd have a much better story. But we don't. But look, the green is good. Hardware keeps going down in price. Software keeps going up. Right now, Google's launching rocket ships to the other planets to get more development. Probably your firm is already there. It's a real problem. Hardware is cheap. The first numbers were done with Jiltine and I from Azul that make an incredibly sophisticated and fast Java virtual machine, probably the best in the industry. And we just found a web store, happens to be Dell Web Store, and it turns out that you can buy this was last May, 64 virtual core, 1 terabyte of RAM server for $30,000. What the hell can you do with a programmer for $30,000? Almost nothing. perhaps you've got an offshore place. You just have to clean it. I just checked, and the 1 terabyte of RAM is now down to 10K, quantity 1. And you ain't seen nothing yet. 2017, you're going to get 3.5 to 10 terabytes on your laptop of non-volatile, persistent memory. Memory addressable, not disk addressable SSD. This comes from 3D NAND, which is being built by multiple suppliers. That happens to be a picture of the Intel one. So the hardware has really changed since System R. And many people are not aware of the impact that hardware has, but it's really critical to the performance of data. Because in the end, if we can get it in memory, the game all changes. The one lesson we've learned over and over and over again, if we can get it in memory, which means the first trick is to cache it because we don't have enough memory, or we can bring it in big segments, or we can bring the whole thing in, we're going to be faster. And even if they're not faster, we're going to have a lot more flexibility in terms of being able to interact with the data and change our computations. So all these things are going on at once, and it's really, really important. And there's two that I really want to dwell on, because I think they're very important for database, and they're certainly very important for our database. One is the huge amount of persistent memory, which I'll talk about. The other one, which I don't have time to go into in detail, is the existence of more and more larger vector instructions. Vector instructions allow you to basically do multiple operations and do those over small vectors that are sitting in the registers, such that vector adds essentially cost no more than a scalar add. Intel in the fall introduced this thing called 3D X-point memory. I apologize for the marketing slide, it's just one that's there. I don't really know whether it's 1,000 times or not, but it is a lot more capable. The exciting thing about this is that it's huge amounts of memory. It's going to enable a petabyte in a rack, 100 terabytes. Most people, if you can work with 100 terabytes in a box, 50 to 100 terabytes, you can do most of the interesting data you want. There are people like Google and Facebook, right? But most of us are not those kind of people. And even they, if they can get an active working set into a box like that, can really run. They're going to sweep from exabytes or whatever they've got, but in the end, the active set that gets used for analysis is usually much smaller than that. So if we can get to something like 100 terabytes of memory, even 10, where we've got the 10-to-1 ratio, we really are living in a different world for data science, for everything for that matter, because all the algorithms and things can change. The other thing about this is that on chip there's compression, there's encryption, so you're really going to get 10 terabytes, 20 terabytes in a 10 terabyte drive memory. And in addition to that, because of the write failure problem, there's now extra gates and so on there, so you can actually do some recovery, so you'll have these drives will last longer. So the failure rates of the drives are improving quite a bit. First SSD drives, I know people in telco business that run around yanking out SSDs and putting new ones because they get write failures. That's improved significantly. What this means is there's a new architecture level where there's new kind of memory in between. This non-volatile persistent memory, HP's going there in 2 or 3 years with memory. There are different technologies, but every major vendor is headed to this space. It means there's going to be a lot more memory, and it's going to be directly processor connected. First using, this is using PCI Express, but it's all going to InfiniBand in the next processor version. So it's going to be much, much faster. The new programming model says directly from my application I can address, I can memory map this memory into my space. I can now directly address it from my program. So I'm not talking about SSD anymore. This is really memory, byte addressing. Lots of it. We did some early work, as of a number of other database vendors. This was early last May, running the stack benchmark. We have the stack benchmark we happen to look really, really good on. You all know about Benchwise. Everybody has one that they do really, really good on. This is ours. I'm not hinting it, just it happened to be one that we ran. Very impressed with the early cut of the Intel hardware, basically. Taking this Intel hardware, we're able to take a classic streaming, trading application, put it together, and run a lot of it using NVMe. Very exciting. The other thing that's happening on top of the storage layer and performance is the fact that we're, many of you used to have NFS, which was always good, available, slow. You can speed it up. You can do a lot of work in NFS on the left. And then you got ZFS, which was great because it got you that compression and speed. There's now a whole new set of file systems that take advantage of these new kinds of architectures, the high speed, the fact that we've got, maybe 50 to 100 gigabit links between these things, the fact that we can, got all this extra memory, the fact that we've got way more processors so we can overlap and compute things ahead of time. So there's some serious challenges for HDFS as a file store now. MapR was one of the first ones bringing in faster file systems. There's a whole chunk of these out there now. And these are designed for this next generation of hardware. And they're going to make a big difference to everyone who does something with data because we're going to get us pages faster off the disk. Of course, we don't have a disk, actually. Well, they'll also presumably handle files. Why do we have files? We've got 100 terabytes of this already. Why do I have to name it within 100 1,000 funky files? Oh, well, forget it. If you have to have files, this is going to be faster. So what does it mean for database? Well, it means that there's a big mismatch between the software and the hardware. Caches, the current hardware has got somewhere between between 4 and 7 levels of cache. Latest PowerPC is 7 levels of cache. Intel, new Intel chip coming out. Programmers don't know how to use that cache. You can't just say cache A, B, C, D. Right? It's based on statistical use. And there are lots of ways you can screw up the cache. So this is really wizard's work. You need Martin Thompson and Todd Montgomery and people like that to do Aeron and things like that to actually figure this sort of stuff. Miles. The problem is that each time you tweak something for the right cache size, like your B-tree index, a new machine comes along and you're SOL. So there's a wonderful set of research into something called cache-oblivious data structures. This is going to be very, very important. Comes from the world of functional data structures, very interesting work. Immutability, very important. It didn't get invented by functional programmers, but it is one of the great properties of functional programming. And the whole notion of having an immutable log or a immutable database gives you lots and lots of leverage because you don't have to pay the expense of updates. You just keep a little clever table that basically says where they're updated. Want to see some really nice work in immutability? I include a look at the work of Rich Hickey and Closure and Baton, which is really wonderful stuff. It's really exciting to see a computer scientist who actually reads the papers first and cites them in his work. Just what a wonderful idea. I thought that had left the earth until Rich started doing it. Reads are cheap, writes are expensive. So immutability is really good. We don't want to update that non-volatile memory. And writes are always going to be slower. So we need to think about designing architectures that can actually exploit that. We need value types because, in Java the big problem is that you can't, with Jill you can get to 32 gig heap, but most Java virtual machines do not support over a 20 gig heap. This means things like Spark and so on have to be completely rewritten to do their own memory management because they can't really use the Java memory management. It's a big problem in Java. The solution, of course, is not to have pointers. Those are called value types, at which point garbage collection and everything is much simpler. I'm not sure when they're coming, probably Java 11 or something like that. Again, I probably won't be around by then. But Java will be, it's no problem, deployment forever. Just like APL. red tape data structures designed for small hot code and cache. Message passing on something like a Haswell, the current generation of Intel, between processors is actually faster than doing a store between processors using the processor bus. We're not leveraging that in our software yet, but we need to. Because as things get faster and as things are running in the cache, when you break from the cache and go to memory on another processor, things really suck, like an order of magnitude or perhaps 2 orders of magnitude in some cases. But all this sounds pretty hard, right? We need, the only guys who can do this are Miles Dalton and Martin Thompson and Todd Montgomery, and you probably know 20 in New York. So there's no problem. Computer science has an answer for this, right? Because the smart people in computer science have figured out that data-intensive programming, ETL, query, search, immutability, MapReduce, working with collections and streams are just a pipeline of transformations. So, welcome to FPMan. You all need to learn functional programming. So, get your Scala hat on, or your Clojure hat on. Right? It's actually great for us because for years we were the only people doing functional programming, and it's actually pretty easy in Q, but everybody else was doing object or procedural programming, so they said Q was hard. It's not what's hard in Q, it's getting your head around the paradigm of using MapReduce and working with collections. And of course, we're going to go through a technology S-curve. Of course, the bad news is that you can get a lot of bad, twice as expensive Scala programmers easily. Because Scala is very complicated. It's designed in a beautiful language, Haskell, a brilliant designer from Martin University for a very difficult problem, which is how to marry objects and functions, which in general can't be done perfectly. So there's some nasty seams. A type system is not quite what you'd like it to be, but it's a brilliant piece of engineering. And I'm really incredible that a university professor actually built that so successfully and has delivered it to the market. And of course, Scala currently powers Spark. Well, the point here is that we seem to have made things very complicated. And if you go to the functional programming meetup, does anyone speak any language you know? The really serious people all took category theory. Go to any functional programming group and they'll say, oh, it's really easy. And you say, well, what about monad and comprehension? Ah, that's no problem. And they explain it to you. You say, I'm going to give it to, I've seen 1,000 of these talks. And they all start off explaining to you, and they can't go 3 sentences before they have to use monad to explain them all. It scares people off. Functional programming makes people feel bad about themselves. Q has that problem too. The programs are so small. People anxiously go, I'm going to type in my favorite program. Boom, 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 boom. And it just blows up. And you go, I'm stuck. I'm doing it one character at a time, one operator at a time. But when you're changing paradigms, you need to do it, right? Basically, because in a functional programming language, just like in an object language, well, you've all heard of patterns, right? You know where patterns come from? They come from functional programming. MapReduce is an operation in a reasonable functional programming language. So are all the other things. But in order to be proficient, what you have to do is you have to learn the kata. It's been far too long since I studied karate. But just like you know your Emacs keys, or VIs. You need to learn the kata of functional programming. Because functional programming is about really working with collections. And I wish people who did functional programming please just get people working with collections. Forget about how pure it is, forget about immutability, forget about types. I know they're all wonderful, but be gentle. Just let them work with higher order functions and collections. If you get them doing that, they'll appreciate how wonderful functional programming is and how concise the programs are. And then you can inflict on them whatever your favorite language choices are about types or other things, immutability and so on. The real thing is we'd like is why, when we can all live in the same memory, can't we actually really intermingle our programs with our data? Why do we have this artificial world of my app and my database? I don't believe we need to have that in the future. I believe that we can have a unified environment. I'll call it a database since this is the database talk. So the database is actually the thing that I do my development in and my application. Another shining example beside KDB is Datomic. In a place where you live, where your code lives, and your data lives. This is a very powerful thing. We unify the programming language so there's only one set of types. One of the big problems, if you ever look at anything that talks to SQL, there are no tables in your programming language. There's no decent time data type. Some languages aren't even decent string data types. We're just so short and impoverished between what we have in the data world versus what we have in the programming language. We need to unify these things. And please, please, instead of taking all the data from your query and shipping it through an ODBC pinhole at great expense, or worse, serializing it into some god-awful big format and shipping it, take the functions to the data. That was one of the big breakthroughs with MapReduce, right? You basically ship the map function, the reduce function, to the appropriate place in the server where the data is, and they execute there. Well, if you can actually run inside your database, you don't have to transmit data anywhere until you're done. So you can just return the results. What an idea. The whole notion of cache, what's cache? It's just data, you don't even need a cache. You know how many bugs are due to handling caches incorrectly, keeping caches consistent, refreshing the caches and so on? Why do we need all these caches? It's just too complicated. We just have memory. That's all we need. It's sufficient. We also want to be able to deal with the fact that data does have missing values, as other things. We want to be able to have property constraints. Property constraints are my friendly word for types. I really want types, but I want to turn them on. I can't imagine using Excel where I have to type the type in for every cell when I go along. That's what it feels like to me when I use Haskell. Bang! Oh, the right type's wrong. I was just thinking. When I run my program, no, the types aren't right. You can't run it. Well, I just like to see some dots. Wrong. You can't do that. You're not allowed to run the program until it won't compile. I understand how wonderful it is if you're a computer scientist. It just really sucks if you're an experimentalist. And it's very hard to do if you're playing with data because you don't really know what the data looks like. If I did, I could write the type specification for it, but I don't. And maybe we'll find a way to leverage machine learning so we can actually figure out what our big data looks like instead of having to waste a whole lot of time doing bad ETL. Simplicity, I think, is defined by a simple language that supports collections and queries. Scalars are bad. We shouldn't let scalars into our language. They're exceptions. If you just make everything collections, life is much simpler. When we teach people how to write queries and how to work with collections, it can be a much simpler world. What does your average mobile app do? It takes a collection from the server, subsets it, puts it on the screen, you select from the collection on the server, and you send the result back. Why does that take so much code to do something so simple? Why? Type? Well, that may be it. It's part of it. There's also a lot of frameworks to help you. The API field of dreams, give them another 100 APIs, it will help. Yeah. Well, Swift is much nicer, which is the new Apple functional programming. So it is functional programming. And if you just add operations like each, which is map, reduce, and scan, which nobody seems to know about, which solves the problem of doing recursive traversals in for drafts or other app trees, then programs actually turn out to be pretty small. So I'll just finish by saying that clearly, I think the best way to do this is to use some sort of vector functional runtime. I'm not sure the one we have is the right one. I know that Arthur doesn't because he's already built another one. And he'll build two, he'll build one every 2 years, which is the wonderful thing of the privilege of working with Arthur Whitney. Basically the whole language, an array language is value type, so there's no boxing and unboxing. There are no scalars, everything's in a box. This is a big expense of an object-oriented VM. It also makes garbage collection very expensive because you have to use a copying garbage collector, which just doesn't work, and value types will never scale with a copying garbage collector. You can support the data machine types because guess what? The data on the disk is rectangular, the data in memory is rectangular, and the data in the cache is rectangular, and the data in the registers is rectangular. There are no funky round things with headers and tag bits and everything all over. Machines don't eat objects, I'm sorry. And if you want to go fast, we do now, we have to try and get close to the hardware because the hardware is not getting a lot faster, so we have to have a better abstraction. Virtual machine can be very, very small. The core K virtual machine is less than 64 kilobytes. I may shock you, the source code and the object code are the same size. Think about that. The arrays are naturally column stores. If APL had thought about this, instead of all the APL programming, we don't do files or we don't do a database because we just do what's in memory. And that was one of the big, along with the weird keyboard. But the big reason was they just didn't do data well. They didn't play in the world of the PC and in the world of database. But there's a natural affinity between column stores, which are just vectors, produces the impedance management, so you can just transfer things. The vectors are turned. Want to be fast serialization? Forget protocol buffers for simple binary transfer if you're using ARIN. To serialize a vector, you copy the bytes onto the wire. Count plus data. Can't get better. Can't get faster. You can slow it down by wrapping it in some other loop. You can go along and you can, because the machine values, you've got access to the direct hardware, so you can leverage things like vector instructions. You can take operations and they stream through data, so this is a natural way to fill the cache. When you're walking through things sequentially, which seems like a naive approach until you realize how important that is on today's hardware. If you can bring this stuff through and keep the stuff that you're working on close to you, you're going to get significantly more performance. One of the problems of compiling things into ultra-efficient query maps and generating all sorts of code with JITs is you cause things to fall out of the cache. If you have a very aggressive JIT, it'll generate so many instructions that it'll cause cache faults. So here what you thought compiling was way better, but it turns out in some cases simple interpreting is actually faster. Very counterintuitive until you look at the way the hardware works. And you start putting these kinds of things like vector instructions on chip, that's only going to get better because a lot of the issues are simulated vectors with software. The libraries in languages like this are not implemented in themselves. Why not? Because it's very hard to do efficient implementation of fast libraries in your own programming language. There are very few cases of that. Haskell's been working at it for years. In particular, there are some wonderful Haskell libraries, math. The problem is that, and when you do that, you have this interference between the runtime and the library. For example, in Java, the same thing is true of C#, but I seem to be picking on Java. In Java, basically, when you add the new functional constructs to Java, which are in Java 9, I think it is, all of a sudden, Hotspot doesn't know about them. Because what Hotspot's the optimizer, right? So it's running this little window, and it's recognizing patterns and instructions. And all of a sudden, you're going on and goes, WTF, I don't know what those are. there must be something weird, I'm not gonna optimize it. So all of a sudden, a library improvement to give you new functionality actually slows you down. So there's an interaction between the libraries in the programming language and the runtime. So you have to simultaneously update both to get this right. And that actually never happens. What you do is you get the first version implemented of Java, and then the next version will have that sped up, or the next version after that, some version. Parallelism is trivially implemented. Anyway, I'm sure I'm way over time, so I'll finish here. Thank you very much for your time.
We're going to take some questions now. Hands? Who wants the first question? Let's see hands.
Corrective remarks are accepted too.
Somebody? That's a first. Oh, you're.
What was the algorithm, the uncertainty algorithm that you mentioned?
The uncertainty algorithm I mentioned is called Dempster-Shaper. The best one we've found in 20 years. We're dealing with representing uncertainty in a numeric way, so you just end up adding parallel vectors that have the uncertainty depending on how many statistical terms you want associated with it. You can compute over them in parallel, so it's very, very good for reasoning.
I have another question.
Yeah.
So out of the kind of the different functional programming languages, one that you think strikes a balance between academia and journey versus usability and
Yeah. So the question was, out of all the different functional programming languages, is there a balance between, is there a language which has a balance between what might be considered sort of academic and the other is maybe very, very efficient but more difficult to learn and cryptic. That assumes that the academic one isn't hard to learn and cryptic. From my point of view, it's actually easier to teach people Q because I live in that world. Q is actually roughly based on scheme. So it's essentially a scheme where the lists are represented as vectors. But I've been living it for a while, and the problem with after you do it for 3 months, you don't understand what the problem is. I would say that probably my language of choice, just wanting to learn, would be Clojure. Clojure or scheme. If you're in software and you've never read the structured interpretation of computer programs, which is called by some people the Wizard's Book, you should read that. Even watching the old videos are great motivation. So scheme is a great place to start. Clojure is a popular commercial language. Unfortunately, it runs on the JVM.
So some of us have to deal with legacy databases. How, in your view, would those fit into the new world that we live in?
So the really important question, many people have are of course dealing with legacy data. You're not dumping it in a data lake or a data swamp. You already have one, it's called a warehouse. So I think the first point is that basically a lot of people are you're moving to new technology to do query. So essentially you can do the data fusion, data federation by doing that. Clearly the challenge is getting it out of the existing database. In a previous life I did high-speed database restructuring. So for some people we do things like read the page tables right off the disk and materialize them in a different database representation. Obviously, you have to. It's a business decision, but I think we've seen a number of people migrate for specific. It's based on the value of the thing to the business. Clearly, some data is going to sit there. Nothing wrong with it being in a good relational store. It's reliable. It's proven. A lot of people, what they do now is we do a lot of log file processing, so people who have data in Oracle or DB2 basically push us the logs, so we essentially we're kind of operating as a query cache in that sense. But I mean, you have to do it responsibly, obviously. I'm not advocating that anybody, even if I did, it wouldn't matter. People are going to live with that data for a long time. Hope that answers your question.
Time for one more question? Hang on.
So you said earlier that all is going to be like one box and there will be no scalars. So can you specify, because networks, they do grow faster than hardware, and what is like overall perspective of network solution connected to K?
So you're talking about running in a high-performance cluster or something like that?
Yes.
There's really, you can put the KDB instances on as many machines as you want. So you can certainly run it in a cluster. There's lots of people who do that. We run, each is a parallel, each operation, so it runs in every core, every processor. Tend to like tightly coupled clusters because the performance between them is much faster. Most people would do that. I think in the future, when you see this high-speed messaging bus, there's an opportunity with a high-speed messaging bus to basically replicate the data very quickly across the whole cluster. I think that will benefit everyone, not just us. There's a lot of talk about shared nothing and so on, but to get shared nothing, you have to get shared to begin with, right? So to do that, you have to do the writes across it. But there's no, we have some very large customers that are working with massive numbers of cores doing those sorts of things. Again, it's a data architecture. We don't offer a magic solution that says, you just do this and it works, because making a high-performance parallel system work, as I'm sure you know, is a challenge. But it's certainly a lot easier than doing it with other technologies, I will say. Same engineering and design activities apply to it as apply to any other technology. It's just because it's a lot simpler, and from my perspective, it's easier to do. That's why I ended up going with it, because I couldn't figure out how to get all the other stuff installed.
That's all the time we have, but Dave will be here for one-on-one questions. Feel free to come up now and ask him. Thank you very much for coming, and thank you, Dave Thomas.